Hello everyone, welcome again. In this class, we will try to learn how to make the bending moment diagram for a cantilever beam with uniformly distributed load. In our previous class, we have seen that how to make the shear force diagram when we are having a uniformly distributed load on cantilever beam. So this was the simplest case we have solved. In addition to that, we have also solved the problem where a uniformly distributive load in addition to the point load is there, and we have seen that how to make the shear force diagram. In this class we will focus that how to make the bending moment diagram when we are having a uniformly distributive load on a cantilever beam. So this is our problem where we are having a uniformly distributed load over the entire span of the beam, and the intensity of the load is 8 Newton per meter. The length of the beam is 4 meter, and we are interested to get the bending moment at point B, bending moment at point A, as well as the bending moment variation between A to B region that we can define at any distance x. So let's start with the point B. As we have already seen that if I am starting my bending moment diagram from point B and uniformly distributed load is starting here itself, that means the net force acting at point B is 0. That means the bending moment at point B will be 0. Such problem we have already considered when we have made the shear force diagram for a uniformly distributive load. So let's now consider another distance x at any point on the beam and write the expression for the bending moment at distance x. So we can see here that for this point, the load which is actually responsible to create the bending moment is this much load. That means the load will be what? The load will be 8 into x. And what is the point of action where the load is acting? So we can identify that this is a uniformly distributive load. So the point of application of this load can be considered as the center. That means I can consider that for this much load, the load is actually acting here and the magnitude of load is 8x, and this distance is what? The distance will be half of this distance. That means it will be what? X by 2. So ideally I can write that my bending moment at distance x, because of only uniformly distributed load, will be what? The load is 8x and the distance is x by 2. So I will get that 8x square by 2. And what would be the sign of the bending moment? As we have already seen that if the bending moment will be clockwise, its sign will be negative, and if the bending moment is counterclockwise, the sign will be positive. So in the given case, as the load is acting in the downward direction and I am interested to get the bending moment here, the sign will be negative. So in this fashion, we can write the bending moment expression for a distance x when we are having the bending moment for a uniformly distributive load. So here I would like to mention that you should remember a formula. Whenever we are having a uniformly distributive load of intensity W, your bending moment will be defined by Wx square by 2. So I would request all of you that please remember this formula, that the bending moment when you are within the uniformly distributed load, please understand, if you are interested to find the bending moment between this length, then this formula is valid. But when you will cross the length, the formula will change. That we will see in our next problem. So for the given problem, when the entire span is having a uniformly distributive load, the formula is valid, and this 8x square by 2 is actually valid up to this end. So here, if I will find the bending moment for point A, the x will become what? The x will be 4 here. So the bending moment will become what? Minus 8 by 2 into 4 square, that is 16. So I will get a value of minus 64. If I will make the diagram of bending moment, again this line is representing the beam. Upward will be the positive bending moment, downward will be the negative bending moment. Bending moment at point B is 0. So here the bending moment is 0 When I am reaching at point A, the bending moment is having a value of 64. But what sort of distribution will be here? Is it a linear distribution? Because in the previous case, when we have solved a problem of a cantilever beam with the point load, the bending moment expression was proportional to the distance x there. You can check my previous video to see this sort of problem, but here if you will cross check, the bending moment is proportional to x square. So in this case the bending moment is actually proportional to x square. That means the variation is parabolic. Therefore, when I am making a diagram or the distribution of the bending moment, there will be a parabolic graph between point B to A. So this would be the expression, this distribution of bending moment while I am moving from point B to point A. At this point, you must understand, we have understood here that the bending moment is proportional to x square. That means the distribution will be parabolic. But why this sort of parabolic? Why not this sort of parabolic? So this is a great confusion. Let me explain you again that we are having a uniformly distributed load in this way, and we have seen that the bending moment expression is what? 8 by 2x square with a negative sign. So as x is increasing, the bending moment is increasing and the distribution is parabolic. So we are having a choice to give the distribution in this way. This is a parabolic curve, or we can also make a parabolic curve in this way. So which is a correct diagram? This is the correct diagram. First you remember that the concave type of parabola is correct. And why it is so? Because another expression that says that the slope of the bending moment give the value of shear force. So at this point, if you will be able to make the shear force diagram, you will know that why the bending moment diagram slope is defined by this diagram. So if you will recall the shear force diagram, this was the shear force diagram. You can check my previous video. In this diagram, you can see the shear force at this point is 0 and shear force at this point is non-zero. What does it mean? It means if I will see the slope of the bending moment diagram, at this point the slope should also be 0. This is the expression you should remember, that the slope of bending moment diagram give the value of shear force. So based on this philosophy, at this point the slope should be 0, and if you will go and check this type of parabola, it is going to give you that the slope will be non-zero here and slope will be somewhat 0 here. But when you will see the second type of parabola, which is the right answer, the slope is 0 and slope is non-zero here. That means this is the right answer. The slope of the bending moment diagram will give the value of shear force. Therefore, this is the right answer. If you are not able to understand this philosophy, please remember that the diagram will be of a concave parabola. This is not the right answer. So I believe now you have understood that how to make the bending moment diagram for this simple problem. Now let's start with the second problem, where the distributive load is not for the entire length of the beam. It is distributed up to a span of 4 meter only. So in this case, I will be interested to get the bending moment for point C, bending moment for point B, and bending moment for point A. In addition to that, I am also interested between the region CB, between the region BA. Again, I will start with point C, and as this is a uniformly distributed load, the bending moment at point C will be 0. When I will move further, again I have to consider a distance x. So let's assume that this is x distance, and I am interested to write the expression for the bending moment for a distance x. So this much load is actually responsible for the bending moment at this point. And as I have seen in the previous problem, that I can assume that this load is actually acting at the center, and the magnitude of this load will be what? This much length multiplied by 20. That means I can consider that this is my beam and a load of 20 into x is acting here. So this is the 20x load. And what is this distance? This is the half of this total distance, that means x by 2. So here also I will get expression 20x into x by 2, that is of negative sign. And as I have seen earlier that if the load is W and you are working within the length of uniformly distributed, you can simply write that the bending moment will be by a formula Wx square by 2. I am not writing here positive or negative sign, that you have to cross check. If the clockwise bending moment negative, if the counterclockwise bending moment, it will be positive. In my case, the load is acting in the downward direction and the point is towards the left side, then definitely it will be defined with a negative sign. So the bending moment will be what? 20x square by 2. And this expression is valid till point B. So if I am interested to find the bending moment at point B, my x will be what? My x will be 4. So I am going to put this x value in this expression. Then I will get the bending moment at point B. Hence my bending moment at point B will become what? 20 by 2 into 4 square. So it will be minus 160. So let's draw the bending moment distribution. As I know that the bending moment at point C is 0, but the bending moment at point B is of 160 value. Here also we have to draw the distribution, and as I have seen earlier, it will be defined by this parabola, not by this parabola. Please remember. So this is the right distribution of this parabolic expression, and the magnitude has become 160. When I am crossing the uniformly distributive load, I am reaching to this region. Now how to write the expression for the bending moment? This is second important concept you should learn. When you are beyond point B, again you are going to write expression in terms of x. So you will ignore the previous x expression. You will write a fresh x expression that is valid till point A. But as you have already crossed the uniformly distributive load, what you can do, instead of considering a UDL, you can now convert the UDL into a point load. So what I want to convey, please understand, earlier this was my beam and I was actually working within this range. So I have considered this and my expression was Wx square by 2. In the second case, I am interested in this region. So what I can do, instead of considering this uniformly distributive load, I can consider a single point load that is defined by the load W intensity and this distance x, which is 4 in my case. So my load will become Wx and its position will be the center of this load. So this will be defined by x by 2. So in my case, the load was distributed up to a span of 4 meter. So I can change this load into a point load. I will ignore the UDL now and I will consider a point load which is acting here. The magnitude will be 20 into 4, that is of 80 Newton, and it is having a distance 2 meter from this end. And this was the B point, so this is also a 2 meter distance. And now I am interested to get the bending moment distribution for this region. So I have considered x here. Let's go back and write the expression for now this x. So bending moment for any distance x between region B to A. So I am interested to write the bending moment for region BA, and my bending moment what? Minus 80, that is the load, and the distance of the load from the point of interest is this much distance. This was 2. So it will be what? X minus 2. This is the expression. Please understand what I have done. Instead of considering the uniformly distributed load, I have considered a point load which is acting here at a distance 2 meter from here, and the magnitude is 80, and I am interested to get the response at this point. So the distance will be what? X minus 2, and the expression for bending moment will be minus 80 x minus 2. When I will calculate the bending moment for point A, so at A, my x will become what? X will become 6. I will put 6 value in this expression and I will get that my bending moment will be what? Minus 80 into 4, that is minus 320. And what would the distribution now, whether it is parabola or linear? So this is the third important point, that when you will see this expression, it is a linear expression. Now we are not having any x square term. It is simply x term. That means the curve will continue, but instead of having a parabolic distribution, it will be defined by a linear line. So this is straight portion, this is parabolic portion, and the magnitude at the end will be what? 320. And as we always say that the diagram will be closed, and this is closing because of the reaction at this end, but generally we don't calculate reaction for this and we simply close the diagram. So this is the bending moment diagram for the given problem. The problem was what? The problem was partially distributed, uniformly distributed load. And what was the important point here? When you are working within the range of UDL, the curve will be parabola, and this would be the expression. When you will cross this, the curve will become linear, and this will be the expression. I believe that this second problem will give you more insight how to make the bending moment, but again I will say you should practice. Let's solve the last problem where we have included a point load in addition to the uniformly distributed load. So in this case I am interested to find the bending moment at point D, bending moment at point C, bending moment at point B, and bending moment at point A. I will request all of you, before you make the bending moment diagram of this problem, you should make the shear force diagram. But here I am primarily explaining the bending moment. In my next class, I will take one example and I will solve the example for both shear force and the bending moment. So let's start with the bending moment at point D, and we have now understood that when the UDL starts from here, so the bending moment at point D will be 0. When I will write the expression for the length C to D, I will first consider one x distance. So the bending moment for expression x will be what? This is the intensity, and I know that bending moment will be Wx square by 2 when I am working within the UDL. So here the intensity is 10, the expression will become minus 10x square by 2, and this expression is valid till point C. When I am reaching at point C, my x will become what? The x will be 2. So I will put this x value in this expression, and my bending moment at point C will become what? I will put 2 here. So I will get 2 to the 4. It will be minus 20 Newton meter. Let's start making the distribution here. So this is my line. This is my point D where the bending moment is 0. When I am reaching at point C, the magnitude has become minus 20 and distribution will be parabolic. After point C, again I am going to consider expression x, but I will ignore the previous x expression. So here I will make another x expression. If you have confusion with the x value, you can consider the x1 for the first case, then x2 and x3 and so on. Again I will write the expression for any distance x which is between B to C. But here, in addition to the uniformly distributed load, this 20 Newton will also come into the picture. So let's write the expression for the first 20. So the 20 force is acting here. I am interested at point here. So the distance from the 20 will be this one, and that is what? The total distance is x. This is at 2. So I will get a value x minus 2. So my expression will be minus 20x minus 2. This is because of the point load. Now what would be the expression for the UDL? As I am still within the UDL, the expression will be what? The expression will be the negative Wx square by 2, but the W is what here? W is 20 here, so I will put a 20 here. So this is the expression, and this expression is valid till point B. So when I will reach at point B, my x will become what? X will be 2 plus 2, 4. So I will put 4 in this expression. So I will get minus 20 into 2 and minus 20 into 8. Finally, the bending moment when I am reaching at point B will become minus 200. So earlier the bending moment was 20 only. Now it is minus 200. That means great change in the slope. You have to make more sharpened slope here, but whether the slope will be parabolic or the linear. So here you can see the expression is mix of a linear term and a parabolic term, so that it will again a parabola but with the larger slope, and you will have the second slope here, and the magnitude at this point will become 200. Please understand, this slope is not important, but this magnitude is important. So when you will solve the problem, you should remember that the magnitude will be 200, even though it is not scaled. This much length is representing the 20 and this much is representing 200. Doesn't matter. This is not a scaled diagram, but the magnitude should be correct. Beyond B, when I am crossing the B point, again I have already crossed the uniformly distributed load. That means I can now make the problem simple now. Earlier this was the UDL and this was the point load. It was of 20 value, and this the magnitude, sorry, I have considered here this the 20. Instead of 20 it will be 10. That means this will not, this will be 10, and your final expression will be what? It will be 120. Please change this value to 120 instead of 200. Doesn't make any difference. If you will solve the problem, the numerical value will be correct in your numerical. But what we need to understand here, this was a 10 Newton per meter load, this was the 20, but I am interested now in region which is beyond the UDL. So what I can do, instead of taking the uniformly distributed load, I can now convert the UDL into a point load. So this was the 4 meter length and the magnitude is 10. So there will be a force of 40 Newton and it will act at a center of this distance, that means 2 meter. In addition to this 20, there is a force of 20 is already acting. That means there will be two force. One is of 20 and 40. So the net load will become what? 60. So now the problem will become very simple. I will have only one load of magnitude 60 Newton and I am interested to get the shear bending moment at this region. This is of length 2 meter. So what would be the expression here? The expression will be simply 60 into x minus 2 because I am interested for this much length. So when I am writing the expression for the bending moment between a region from B to A, my expression will become what? My expression will become 60 into x minus 2 negative. And this is the expression for the bending moment of any distance x between B to A. And when I will put the x is equal to 6 because it is the value of x when I am reaching at point A, the bending moment value will become what? 6 minus 2 4, 240. So that beyond this line, this will be the linear curve and it will reach to a value of 240. Please understand, for the first two case, when I was working within the uniformly distributed load, the slope or the curve is represented by a parabolic curve, but beyond this it will be a linear curve. And please remember, I have made a slope which is less than this slope, but it will not be the case. The case will be that the straight line, but it will be in the continuation of the previous two slope. So we can make another diagram which will represent the entire bending moment curve. Earlier it was 20, then 120, and then 240. This would be the actual diagram where this is a parabolic curve, this is also a parabolic curve, but this is a linear curve. So I believe these three problems will help you to understand how to make the bending moment diagram for a case where cantilever beam with uniformly distributed load. And generally the problem will be a partial load, not the complete span load. In the case of complete span load, the problem will be very simple, but when you are having partial distributed, uniformly distributed load, so you need to take two consideration. One, when you are working within the UDL, and then you will cross the UDL. With this note, I am closing this session. Next time I will bring a numerical. We will solve the complete numerical to reinforce the concept of SFD and BMD for uniformly distributed load on a cantilever beam. Thank you.